Well, we might as well, I guess. If we're really punctual, we start 15 seconds early.
Unheard of.
And that way people coming in can feel guilty.
Yeah.
So I don't really need this because I know David quite well. He's except that one thing I didn't know you had an aerospace engineering degree in 2003 from North Carolina State University.
Yep.
Is that right? Yeah,
that's true.
With summa cum laude.
That's right.
And so that explains some things because he's interested in kind of space mission activities, you know, and trying to get some spacecraft out there, especially to the Martian moons that he might tell you about later. There's room on his schedule if you want to meet with David. He's here for this theoretical astrophysics program, TAP Colloquium. He's here for the week. So we're very lucky to have this budget to bring in esteemed visitors for the week so they can enjoy Tucson weather and meet with people and cross-pollinate ideas. And you're on sabbatical?
I'm on sabbatical, so I'm here to like just hang out and collaborate. I actually have a QR code to the sign up at the end of the talk, so stay tuned to the bitter end. You can get a direct link.
So you can waste all his time for a week on end. He's on sabbatical. And then in 2005 to 2009, he was here as a graduate student, and he was a student of Brandon Malhotra studying the collisional and dynamical evolution of the asteroid belt. I guess mostly dynamical.
At the time, yeah, it was dynamic.
And then got interested that these things bang into things, and that became a very interesting piece of work. And so David is known as being one of these dynamical modelers who really cares about geology and what these dynamical dots do to planets and in the formation of planets and the evolution. Now he's a professor at Purdue. He moved there in 2011. In between, as many of us have to do, he spent a year or two with Bill Bottke and Hal Levison. And
yes, them specifically, everybody should spend 2 years with Hal Levison.
It's an essential part of a dynamicist's career, and it's been instrumental in building up Purdue into one of the preeminent planetary science powerhouses today. And so today he'll be telling us about modeling collisional fragmentation. Oh, there are computational classes. Is this on the QR code as well?
Yes.
Okay, he's teaching a couple of techniques seminars tomorrow and Wednesday for any of you or any of your students who want to learn how to run state-of-the-art dynamics codes and make cratered landscapes using.
We're gonna make these movies.
Crater Maker. All right, take it away, David.
All right, thanks a lot, Eric. I really appreciate. It's really, really great to be back here. I haven't actually been in this room since I was a student, and when Professor Bill Hubbard was on this side and I was on that side, so it's been a while. So it's really, really great to be back. And I actually am going to refer to some of my time as a grad student here, so stay tuned for that. So a little bit about myself and my group. Since joining Purdue, as Eric has said, I have been working you can kind of divide up my work into sort of two domains. One is on n-body modeling and the origin of planetary systems and satellite systems. The other is on cratered landscape evolution, looking at how do cratered landscapes evolve over time. And so you can kind of divide my work into two kinds of codes, because I'm a modeler. So I write code and use software to answer questions about the origin and evolution of planetary systems, always with an eye to data constraints. And the n-body code we're developing, which we're going to do a workshop tomorrow on, is called Swiftest. The landscape evolution code is called Crater Maker. It's an offshoot of an older code called CTEM. I have a workshop on that on Wednesday. And these are sort of a collection of the grad students and postdocs who've been through my lab, both former and current, who I have to acknowledge because they've done a lot of the work to sort of develop some of these projects into full-fledged papers and code and all the good stuff that you're seeing on the screen. Okay, so my interest in this, what is it that kind of combines this dynamics, the n-body modeling and the orbital mechanics with cratered landscapes? And it actually goes back to my time here as a grad student. So I started in 2005, and there was a paper that had just gotten published in Science, led by Bob Strom, who's still he's still listed on the faculty. I know he's probably in Japan, but he's still out there kicking, which is great. And my advisor, Renu Malhotra, she was a co-author in this. This is a paper I'm going to talk about a little bit later on, but this was a paper that they were taking the cratered landscapes of the Moon, Mercury, and Mars, and matching them up with, at the time, the newly sort of worked out size distribution of asteroids, and finding that there was a really close match. The ancient terrains had the same shape, size, frequency distribution on this R plot as the asteroids. And with Raynu's help, they sort of came up with a story, a dynamical story about how you actually get asteroids out of the main belt through a non-size dependent mechanism to actually make this happen. And that actually formed the basis of a lot of my work in my dissertation, working out how planet migration can sweep through asteroids, right? So I like to always use this analogy that the craters are like a fossil record of ancient small body populations. And if you can interpret that fossil record, you can actually try to understand something about not just the population, of objects, but also like their dynamics, because that kind of leaves behind a signature. And just as a velociraptor turned from, this scaly lizard thing to basically bird, a good fossil record can really help you understand and make your models better. So that's what I've been trying to do with my career, is to kind of piece together these two things, the dynamical models and the physical remnants of these ancient populations left behind in craters. Now, I'm in the right place, I think, to tell you that collisions and fragments in the solar system are important. I shamelessly stole these off of Eric Asfog's Vimeo from years ago. These are some SPH models of the collisional outcomes in like the origin evolution of planetary systems, different scales. One's on Mercury and one's on Psyche. So collisions and debris that's produced by collisions is a really important part of this process, and it's really the thing that links together craters and dynamics, right? So the understanding of and the observational constraints we have on collisional processes during planet formation, particularly, is really seeing a renaissance right now. So I was here actually a couple of weeks ago to this NORLAB conference, and some of the results I saw there are really, really great. So we now have ALMA, JWST, things like the Gemini planet imager. So we're actually capturing data of real systems that up till now all we could do is in the computer model. So this is one of my collaborators, Alan Jackson, did these numerical models of basically what the aftermath of a giant impact, like you see in these SPH simulations, N-body, what do they look like, ways that we could observe. And we're now starting to piece together like observations. We can directly actually see these. And not only that, but we're starting to see the evolution over time, like the JWST and GPI are like, can actually see differences from the older ALMA data. So we're actually seeing these things evolve in real time. It's a really, really exciting time if you're interested in the dynamics and evolution of debris disks. Now, as far as like that connection between the craters and the dynamics, if we go back to our own solar system, one of the things that I think it's really important to keep in mind is that a single impact can have a huge effect on the population of objects. So this is a simulation I did as part of a project I was actually working on with Alan Jackson and Eric here, where we're looking at the debris of the remnants of the Borealis Basin impact on Mars, the big impact crater on Mars. And the color coded here by ejection velocity. So the warmer colors are faster speed ejecta, and the cooler colors are lower speed ejecta. But you can see like this population very quickly sort of mixes into the near space and becomes the things that the impactors that can make the planets hit the planets. And the numbers can get pretty big pretty fast. Like the one impact here can actually make as much debris as the entire NEA population, right? And so you're basically, depending on what that debris looks like, its size distribution, how much mass is in there, and how it actually accumulates in the ejecta. This could potentially contribute quite a bit to the cratering record if there are surfaces there to record them. Okay, so a lot of what my talk is going to be about is about, if you saw the title of my talk, it's, breaking up is hard to do. That's my old play on words, because the modeling this in any kind of consistent way is really, really challenging. So I'm an N-body modeler. I started in Raynu's group doing a lot of work with N-body models. I love N-body models. They're very elegant. Solar system N-body models, though, because of the basically how many dynamical cycles, how many the dynamical age of the solar system makes it really challenging to model very large numbers of particles. So in a typical sort of planet forming simulation done with these N bodies, some Plankett models, things like rebounds, Mercurius, Simba, Mercury, et cetera, we typically model in the order of a few tens of thousands of particles at most. I mean, computers are getting better, but this is an n squared problem, right? The amount of computational effort goes as number of particles squared. And it's really hard to beat that down. So one impact, so this comes from the classic picture. Ooh, go ahead. All right, let's go ahead. Okay, hit the wrong button. Trying to hit the laser button. Okay. All right, so one collision, this is from the Leinhart and Stewart 2012, which we reference quite a bit here. One of their collisional outcomes, so it's a 1 to 4 impactor to target mass, head-on collision. It makes one big remnant here. This is the largest remnant, second largest remnant in this population here, and it's got a very steep size frequency distribution. So one impact can lead to hundreds, if not thousands, of particles, and there might be thousands of these impacts, right? So the numbers get really big really fast, and so we have to find shortcuts or techniques to sort of get at this problem. Try to get the dynamics without actually modeling the dynamics. So it's a really challenging numerical problem. So this is a couple examples from John Chambers' Mercury code, where they've basically showing that it does matter. Like, you do change the time scale for how long it takes to make planets if you include fragmentation. Their fragmentation model is very crude. Basically, anytime there's a collision that could disrupt, you add a few particles, not too many, you give them some velocity, some percentage of the escape speed, and then you just let them go. And you can see that in this case, this is no fragmentation versus fragmentation. It takes a little longer to make the planets. They kind of ultimately do the same thing. There's more particles stay around for longer. Matthew Clement, a few years ago, did basically similar kind of code, just more fragments, showed that the eccentricity and inclination evolution of, in this case, Earth and Venus, inclination of Earth and Venus is different. If you have fragmentation particles, because you get dynamical friction that helps dampen the orbits of the larger bodies. So it does matter, but it's incredibly difficult to model directly. Another approach is one that's taken by my postdoc supervisor in his code, LIPAD, the Lagrangian integrator for planetary accretion dynamics, is to have basically your collisional fragments not modeled as individual bodies per se. You have individual bodies that dynamically evolve on orbits, but they represent statistical collections of larger things. So you can kind of, if you're familiar with IRPIC codes, which were sort of pre-N bodies and Plankett integrators, was what people use. There's sort of particle in a box, sort of statistical mechanics approaches. You kind of use that in combination with N body, you can kind of use the best of both worlds. And that's kind of what LIPAD does. It also includes effects of gas. This paper that came out with by Kevin Walsh and Hal Levison, just showing you that if you include the effects of dissipating gas dust and collisional fragmentation, one of the big differences between these kind of simulations is that you can actually get to the oligarchs of your oligarchic growth to stabilize and not have a lot of collisions for a while. So they get to when the gas dissipates and the system kind of reaches its modern state, you get a bunch of embryos that kind of sit around and don't do much, and then they eventually go unstable and collide. So you get this quiescent period between when the gas goes away and when sort of collisions start up again. And that is kind of interesting. Again, hinting that we really got to model this. We really have to understand the fragmentation problem because it's really important to understanding how to model these systems. Okay, so that's going to take me to what I did. I don't recommend anybody do this. So how did I get to where I am now? So I maintain a software called Swiftest. We're going to, if you come to my workshop tomorrow, you get a chance to learn how to use it. Swiftest is something that I started actually when I was a postdoc with this guy. Before he was a Lucy PI, he was my postdoc supervisor. And he used to give me lots of kernels of truth and wisdom like this. We actually, when I was a postdoc, this was 2009 to 2011, he was really wanting to make Simba and Swift more efficient and take advantage of parallel processing. So we actually worked in tandem while I was there to sort of make a parallelized version of his n-body code, Swiftest, Swifter Simba. We were very disappointed in that result. And although he incorporated some of the stuff for LivePad, I'll show you in a bit, it was a little disappointing. Many years later, I kind of started working on this again when I had some students, and then COVID happened. And then while everybody else was making sourdough and going down the right-wing rabbit holes or whatever it is people did in COVID, I was like working on code and working on this thing that took over my life. I had got tenure by that point, so I do recommend you start projects like this after getting tenure if you can. All right. So this is going to show you like what we managed to accomplish here. So what I'm going to show you here is a little bit of sort of computational stuff. This is the bona fides of Swiftest. So this is a plot showing a parallel efficiency. So if I was to take a model of planets interacting, in-body simulation, if I have really good parallelization, that means that if I add more process to it, I make the code faster. The amount faster I make, if I did this perfectly, would be this dashed line. So that means if I have 10 processors crunching the numbers, the code is 10 times faster, and so on and so forth. And you see, this is what Hal and I did when I was at Swery, and it's pathetic. This is terrible. Not only that, but like Swifter, which is the code I was using, even one processor, it's like 15-20% slower than Swift, which I always found amusing. They made I think they made an error in code architecture. They used linked lists and they should have. So actually Swifter is a little slower than Swift. Now the parallelization, because you're basically parallelizing the interaction steps, the sort of the gravitational interactions between pairs of bodies. The more bodies you have in your simulation, the more you can leverage that, and the code doesn't go faster in an absolute sense, but in a relative sense can be faster, right? So as I add more bodies, the parallelization efficiency goes up. But I never, even with like 16,000 fully interacting bodies, which is kind of pushing the limits of what people think about, especially 15 years ago, factor of 5 speed up at best. You have to chuck 24 processors at it, and you don't get any benefit for having more. It's just kind of sad. This is why we kind of stopped. All right. So during this COVID lockdowns, and I'm on Zoom with my students, and we're just like, trying to keep our heads above water. I actually did a lot of digging around the code, and we found ways to actually make it way more efficient. So this is Swiftest. This is our new code, and you can see that in this case, I'm plotting a couple different lines here. One is relative to Swift, the original Fortran 77 code, and then the slower Swifter. And you can see that green line again is Swift. And so we're able to get close to one-to-one parallelization efficiency for large numbers of particles. In fact, I can get like 10 times efficiency for 16 processors. Right. So I'm happier with how that's going. There's probably still room for improvement, particularly in Simba when it comes to checking for close encounters. It's a big bottleneck in the code, but working on that. Okay, so now that we have this more efficient code, one of the things that you learn when you do this sort of stuff is that you make the code more efficient. That doesn't make your problems go faster. It means you can throw more particles on it for the same amount of time. So it doesn't actually speed anything up. It just allows us to do higher fidelity simulations. Oh, I want to take one aside. This is something that's been bugging me since I was a student here. These particular n-body codes traditionally don't do post-Newtonian correction, GR, general relativity. Even though Sahan Tremaine wrote a paper on how to do it in '94, nobody bothered to incorporate them in the codes, and it's kind of bugged me. So it's really not that hard. There's a little bit of math you have to do, kind of connect the dots between the paper and your code. But I managed to do that. So right, by default, Swiftest always says GR turned on, and so I'm showing the Mercury precession problem, the classic test of general relativity. If I plot the JPL horizons ephemerides, and they use a different style of integrator that's more precise for short-term orbits than what we use, which is good for long-term stability. And we match the precession of Mercury really well. So this is really important for exoplanets because a lot of close-in exoplanets are close enough that GR actually matters. The precession rates of planets is affected by being really close in. Okay. So on to fragmentation. So now we have this more efficient code. We can start thinking about the fragmentation problem. We can actually talk about how far can we push like a direct n-body fragmentation model. And the one thing that also bugs me about the previous attempts to do this is that they don't do a really careful job of matching the outcomes to the physics. And I'll go through a case sort of step by step what I mean by that. So this is kind of the starting point. This is how you start with fragmentation modeling. Zoe Leinhardt and Sarah Stewart had a couple of papers. Leinhardt Stewart and Stewart and Leinhardt is a pair of papers which they map out this sort of region of space that if you have two bodies collide with different masses and different mass ratios, different velocity vectors, the B factor, like how offset the impact is from the center line, you can then predict what kind of impact outcome you have, whether it's a merger, whether it's something that's breaks apart, a hit and run, and different flavors of things. And then they also include sort of models for what the outcomes look like. What is the mass of the largest remnant? How big is that? What's the mass of the second largest remnant? What's the total mass in the fragments that are left? How much energy is lost? During these, it's an inelastic collision, so you're going to lose some energy to heat. So how much do you actually lose? So they're all given by this. We simplify this map a bit. Most of the things ultimately just go to merger. It's really not whether you have a graze and merge. Just going to ultimately get you a merge in most cases, although devil's always in the details. So we kind of simplify this map a bit. I've been paying attention to this guy, Enzenhuber, Alexander Enzenhuber, who I understand was here around this time, has been putting together this great new library called CoResolve. It's one of my goals this week is to actually talk to the folks involved in that about connecting up and getting those things working together. So once you have the collisional outcomes, then you have to say, okay, what, now that you know what regime you're in, some of the basics, what do the trajectories look like that come out of that? And that's where I think a lot of the other codes have not done a great job. One of the challenges, of course, is that we cannot, there's just no way with a pure n-body code to capture the correct number of particles, the correct size distribution. Not unless you want your one collision to, and I've had this happen, one collision makes 10 million particles just because of size distributions are steep. And so now your simulation is running in real time. And I don't have a million years to wait for a million years to transpire on my computer. And so we have to make simplifying assumptions. So one of the things is we have to have some prescription for reducing the total number of particles to something that's tractable for the n-body. So I've done something which I think is sound in the sense that it captures things like bigger collisions make more particles, but not too many. There's some user-defined parameters to help sort of tune how many fragment particles you get overall. These are all a little fuzzy. We're still kind of working through how to set these in the best way. But then what our collisional outcome model Fraggle does is then once you've decided how many particles you're going to get, we initialize the vectors of the new particles. Now, the thing that we've tried to do really carefully is to make sure that in a collisional outcome, your particle population has the angular momentum, linear momentum, and energy that you expect, because you don't want to be artificially injecting energy or momentum into your system, right? So that's was a real key component that I was really fussy about, is that we have to make sure it's the basic physics is sound, right? So we're not adding or removing energy in the system artificially. So in order to do that, you have to track spin. So you have to keep track of spin, angular momentum, and orbit angular momentum, and energy, and binding energy. There's a lot of sort of bookkeeping things you have to track in order to make all this hold together. And so the way it's designed right now is that we're very strict about conserving momentum. If there's anything about n-body orbital dynamics you'll ever take away, is that momentum is conserved. It's like system momentum. There's very few situations which things are being torqued. And so momentum has to be, angular momentum has to be conserved. Energy is a little more loose. You have to at least lose energy. These are inelastic collisions. So as long as we're losing energy in the collision, we have a target amount we're going to lose. But we're happy just to make sure that we don't gain energy, and that would be bad. Okay, so the other thing is I want to make sure that the trajectories make sense for the kind of collision you have. So when it comes to things like depending on the regime, we're going to initialize the particles in different ways. So this is what a sort of normal disruption regime. It's a bit like a cratering type of collision, where the largest remnant is mostly intact and you get a smaller population of fragments. We initialize them kind of pointing away from the impact site. So this is an example. These are, what I'm going to show you here are actually movies made with Swiftest. Swiftest uses Simba, which is uses a time step reduction, like a recursive subdivision of the time steps. So I basically pull out the subdivide time steps so you can actually see the dynamics during the collision event. So I show you the spin here. So we always have spinning bodies. You can kind of see this is what a disruption type collision looks like. We also have super catastrophic. That's if you have enough energy, you completely blow apart both bodies and you produce a cloud of fragments. I initialize a population of fragments pointing away from the impact site. It's important to keep in mind too is that these are not, there's some Monte Carlo going on here because they're without running a full SPH model in every single collision, which is obviously not going to be tractable. We have way too many pre-parameters for the number of constraints we have. So this is we're kind of relaxing a solution iteratively with some random number kind of injected in there to sort of capture the natural variability of it. So each outcome is going to be a little bit different, but it's going to have the same kind of thing. Oh, these are also 3D. I'm just plotting a slice through it, but you can kind of see bodies kind of expanding in all directions here. The cool thing I like too is the hit and runs with fragmentation. So I think Eric's going to like this. So I spent some time trying to match like what a hit and run with fragmentation looks like. I'm going to show you an example where we have a lot of spin. So I was really careful to try to make sure that if you've got spinning things that you get outcomes that make sense. If you have a hit and run where the runner is like nearing the breakup spin rate, and so you'll see it hits and then you get some residual momentum going on. So you see a little twisting of the particle cloud as it goes up. So all of this is to basically ensure that when we initialize new particles, that they make sense, that they have the distribution of velocities and spins that make sense for the collision that you had, so that you're not sort of artificially inject, because you're going to be having thousands of these collisions. So you want to make sure that you're not just chucking in like wrong physics constantly. I don't like that. Okay. There are some user-defined parameters that help kind of scale the collision results. This is one thing we're still working our way through to what numbers to actually use. It's not obvious yet how to do this. Because you could either have like runs that take years to run or runs that take a day and they don't really capture things. So trying to find that middle ground. We also have to care about spin barriers. So we don't want our particles spinning so fast that it's non-physical. So we have some prescriptions for what do you do, and a merger was going to result in something is spinning too fast. We just treat it as hit and run at that point. So you have pure hit and run. You have a merge where new body is spinning with the combined angular momentum. And if you would have spun too fast, you just make it a hit and run. A lot of edge cases we have to worry about. So this is an edge case. What happens if four bodies all hit each other all at the same time in the same time step? Well, we have to model that. So those are all ticks. A lot of edge cases we're modeling, a lot of computer stuff that not everybody is going to care about, but we're really careful to try to get all this stuff right. Okay, so now I'm going to go into some of the applications of this. So what are some of the problems we're applying this to? I'm going to switch gears a little bit and tell you about some of the work that I've been doing on modeling the origin of Phobos and Deimos. This is something that I've been working on for a number of years before the Swiftest project. So some of this stuff is kind of predates when we started building Swiftest, but it'll become relevant why we need the collisional models as we go. So this is Phobos and Deimos. This is our Mars's little pair of potato moons. So I always like to ask this question because depending on the audience, I get all kinds of answers. Where did Mars get its moons? What are these things? Anybody have any ideas? It's okay. Like you've just barely. I heard that they were. Anybody? Goodness.
Captured asteroids.
That's a good answer, and that's not true. Not captured asteroids. All right. I'm going to say that pretty definitively, even though like if I was on the MMX team, which I'm not, the Martian Moon Exploration Mission, I would have to say we got to test whether or not they're captured asteroids or made a disk. You can blame the Viking mission spectroscopy group for coming up with this idea. It doesn't make any sense dynamically, but to have a flat featureless spectrum in 1977, that's basically carbonaceous asteroids, and that's how that came to be. All right, but dynamically, and we knew this even in the early 80s, this doesn't make sense. So this is really, it illustrates this well, I think. This is a plot of the eccentricity inclination of a bunch of moons across the solar system. And there's really two clusters of moons: regular satellites, regular moons, and irregulars. So regular moons have low inclination, prograde orbits, low eccentricity, and the thing that you can't see on this plot is they're also tend to be really close to the moon, so they're tightly bound. So they're deep in the gravity well of the primary, prograde, flat, equatorial, low eccentricity. And when you see flat, low eccentricity things, low inclination things, that says disk. They're made out of a disk, because disks are highly dissipative, so they always relax into flat ring shapes. Whereas the things that we think are captured, the irregulars, which are these things, they are more often than not retrograde orbiters. So they're going around the opposite direction of spin. They have really just wild inclinations all over the place. So inclinations going, 45 degrees, 20 degrees. Very rarely do you find them at zero. Eccentricity is just they're elliptical. They're also this doesn't plot on this plot, would be another dimension. Tend to be very far from their primaries, right? These are the things that we think are probably captured planetesimals during some giant planet instability, if you believe Hal Levison, and the Nice model people and Lucy team and all that. The regular satellites, and Phobos and Deimos are plot right there. They're down here. In fact, they're some of the coldest orbits of any of the regular moons, dynamically coldest. Okay, so I think Phobos and Deimos are a really big deal. They're really important. They are 2/3 of the moons in the inner solar system, by number, right? Not by mass. Actually, I plot them here. Can you see? Yeah, to scale. That's both of them actually. Phobos and Deimos are plotted here. So yeah, not by mass, but by number. They're the majority of the moons. So they're telling us something really important about the inner solar system and how moons get made down here. And I actually think that the story of Phobos and Deimos is surprisingly close to the story of the Earth's moon. And I'm going to just take a few little differences in starting conditions, and you get potatoes versus beautiful moon that we write poetry to. Okay. So again, coming back to some of the folks in this room, one of the ideas, kind of a starting point, is that there was a giant impact, just like on the moon forming impact on Earth, just scaled way down. And a hypothetical particular impact that actually makes a lot of sense is the impact that formed the Borealis Basin, the big northern hemisphere feature, which Jeff Andrews Hanna and one of Eric's students, Margarita Marinova and Francis Nimmo and colleagues, all kind of came out with a series of papers all at the same time in 2008, proposing this for various different reasons. And I think it makes a lot of sense. If you took away the Atharsis bulge here, this later volcanic construct, you have this elliptical depression. It looks a lot like South Pole Aitken at the moon. So it's probably is like a big impact. And when you have impacts at the scale, where you're distorting the primary as collisions happening, it's a way of like trapping material in orbit. And this is a simulation, an SPH simulation from Kyoto, a member of the MMX team, showing basically how the aftermath of this scale collision leads to this eccentric debris disk that will eventually cool down into a equatorial debris disk. Okay, so the starting point we're working with here is the aftermath of the Borealis Basin. It's a bit like the moon forming impact, but much, much smaller, much lower angular momentum as your starting condition, but you still have a giant impact debris disk. Okay, so there's an interesting phenomenon that I'm not going to have time to go through in detail, but we've published a couple of papers on this, so I can refer you to Hasselbrock and Minton 2019. If we look at how rings and satellites interact with each other, the quintessential world that we always look to is Saturn. So Saturn has rings. It has these little moons that orbit really close to the rings, Pan, Atlas, Janus, and Epimetheus. Saturn's a very rapidly rotating planet, and so the synchronous orbit is inside the rings. Tides always drive you away from the planet if you're outside the synchronous orbit. But also you have something called Lindblad torque. So if a moon accretes at this outer edge of the ring, which they will because the rings are spreading through what's called viscous spreading. So material will collect here where it can actually collapse into a moon, and then both tides and Lindblad torques pull you away from the planet. If you put a ring around Mars, you got a very different kind of situation because the synchronous orbit, the geostationary orbit at Mars, is way farther away from where you would expect rings to be at the Roche limit. And so if you were to do the same thing, you make a ring around Mars and put a satellite there, oops, getting ahead of myself, you have this competition between Lindblad torques and tides. If your ring is massive enough, Lindblad wins. The ring will eventually decay because viscous spreading is draining it onto the surface. Eventually the ring decays enough that tides take over and you switch directions. So you get a cycling behavior. And we demonstrated this in Hasselbrock and Minton 2017. The paper came out in Nature Geosciences, led by my former grad student, Andy Hasselbrock. So we start with a notional debris disk. So on the left-hand panel is the surface mass density of a debris ring. We have a simple like hydrofluid model for the rings that's interior to the Roche limit, and then a simple model for satellite evolution outside. So we begin with a ring. Any material outside the fluid Roche limit will accrete into a moon. Little moons can survive interior to that because they have some cohesion and friction. And so you'll see that our model predicts you get this cycling behavior. You make moons, the moons accrete with each other, they build up, the ring is losing mass, and eventually it loses enough mass that moon switches direction and goes back, and you can get like this cycle over and over and over again. So in this model, we propose that Phobos may just be the last of a set of maybe half a dozen of these cycles where Mars had a ring gave birth to satellites, the satellites interacted with the ring went away, satellites went inwards, turned into another ring, each time getting smaller and smaller and smaller until you've whittled away down to the Phobos that we see today. All right, so that was our hypothesis, that Phobos is participating in this ring moon cycle, and that Deimos in this model would just be whatever happened to, in that initial debris disk, get trapped outside of the synchronous orbit, because once you're outside the synchronous orbit, there's no way to bring you back in. Well, at least our idea was. Okay, so this was a good starting point. It was an interesting hypothesis. There's a lot of issues that we were aware of for this. One of the persistent issues is that like we never fully get rid of the ring, but there's probably other things like non-gravitational, like solar Rykowski and various things that we're not accounting for. I think we'll probably take care of that. We're working on it. We're actually funded to work on that right now. The other thing, which was pointed out to us in a paper, came out just after this one by Robin Canup and Joan Simone. What they showed is that they did a very similar kind of model, except this time they took their fluid ring models, very similar to what we had done, and they married it to an n-body model, SIMBA. And so what you're going to see here is a very similar thing, except this time we're doing fully n-body here and then this ring model. So they put all these particles out here, and they start with a disk that's like ours starting point. You make a whole bunch of satellites like we do. But before you can actually start initiating the cycle, the innermost moons accrete the outermost ones. So there's nothing left beyond synchronous because they get scattered and accreted onto the inner moons. And so in their model, they showed that you never get any material that stays beyond the synchronous orbit, nothing low enough mass anyway to make Deimos, unless you start with a much, much lower mass disk than we did. Too low to really kind of initiate the kind of cycles that we were talking about in our first paper. Now, the thing about this model, though, is that in their SIMBA numerical model, When two particles collide, they always merge. There's no collisional evolution, no collisional fragmentation in here. So what happens if you include collisional fragmentation? Well, I'm going to tell you about a little phenomenon that my colleague Matija Chuk and I wrote about just a couple years ago, which is relevant to this. It's called the Sesquinary Catastrophe. And I love the name of this. It's a really evocative name. So show of hands, who knows what a sesquinary impactor is? Okay, good. Like 3 people. Okay. This was a word that was coined by Kevin Zonley, I think 2007, I'm guessing. You know, a primary impactor is something coming from heliocentric space, hits a body, and makes a crater. That makes ejecta, and if the ejecta is lower than the escape speed of the body it hit, it lands back on the body as a secondary crater. But if you have a satellite in orbit around a primary body, you can actually have a situation in which the velocity of the ejecta is fast enough to escape the satellite, but not fast enough to escape the primary. And so it stays in orbit around the primary. And if it re-impacts either it's the same satellite or another satellite in the system, we'll call that a sesquinary impactor. It's a sesquinary, it comes from a Latin word that means 1.5. So it's like faster than a secondary, but slower than a primary. It's this kind of in-between speeds. What Matija showed in this paper a couple years ago is that if you have a small satellite and its orbit is a little bit inclined or a little bit eccentric, I'm going to show you an example of an eccentric satellite here. When the sesquinary ejecta goes into orbit, it's going to adopt the orbit of the primary. It's going to be really close to that orbit. So it's going to have a similar inclination, but with some spread on it because velocities distributions being with Earth. Over time, those orbits will precess differentially until like they are forming this cloud. And so the actual returning velocity is modulated by the this angle here, right? So if you precess around, that means that if you're hit in your opposite phase, your speed is now faster than it would be if you were stayed in phase. So that increase in the returning speed, if you have a small enough body and the conditions are right, and those conditions are defined by actually a parameter called Q, that number Q is greater than 10, that means the re-impacting debris produces more ejecta than its own mass. So you get a runaway collisional cascade. Each time you have a collision, you're creating more debris that can then feed on itself and make more debris. And eventually you'll blow apart the moon. My student Casabana, we just had a paper, it's under review right now. We're actually modeling this because we did a theory paper, now we're modeling the n-body. So this is showing the Deimos situation. If you put Deimos, give Deimos a little higher inclination than it has today. So Deimos's inclination off the Laplace plane is about 1.8 degrees. It turns out it's actually just under that like Q threshold. If you gave it a higher inclination, you see that it just starts colliding and producing fragments. And it eventually whittles away down to nothing, into basically a Roche exterior debris disk that's inclined or has some inclination, right? Now, it can't stay that way. Collisions are very dissipative. And as I said earlier, once you have a debris disk, enough collisions, you're going to drive it down to a polar orbit. So eventually it will dynamically cool itself down to a lower E&I orbit and it'll reaccrete again because it's past it's outside the Roche limit. So this means that if you have debris that stays in this an inclined or eccentric orbit in this Deimos zone, it can do its own kind of cycle like this, right? It can actually stay as a debris ring until it cools down. So we ran, so this is the same initial conditions as in that Kenup and Salmon paper, my student Hasa, we're working on this right now. But now we turned on Fraggle, our fragmentation model. I put Deimos where it is today, I'm plotting inclination. You see that this region on the outer edge of the disk doesn't just accrete stuff, it's actually highly collisional. So you actually often produce big clouds of debris in the Deimos zone. So even though, in the Kenup and Salmon model, this stuff would have accreted and then gone inwards and then it just kind of eats itself up. But we actually produce these clouds of debris that then we proposed could go through this Sesquinary catastrophe and reaccrete into like a Deimos-sized thing. All right, so I want to revisit the moon. This is my second application. We're going to sort of finish up here. I've got just a few minutes to wrap this up. So I want to revisit this thing. Because I think this is a good illustrative point of what it's like to be a student and not be a student anymore. So when I was a student here, Strawman 2005 was really a foundational paper. They proposed through this paper that because of this match between the size distribution of the impactors that would have made the craters and the asteroids that they're kind of connected, that implies some sort of size independent mechanism to getting at main belt asteroids out and into planet crossing orbits. And they proposed the planet migration. The giant planets migrated early in the history, swept through the asteroid belt. And my whole dissertation was on sweeping resonances through the asteroid belt because, I'm trying to like model this, right? Okay. When I started at Purdue, there was a colleague, actually a former LPLer named Jim Richardson, who had this collisional evolution code called CTEM. And I decided I was going to use this problem to do this thing about the fossil record, all that stuff. And so I thought I'd start with the Strawman 2005 results. I'm going to start there, to verify that it all works, and then move on. But I wasn't able to reproduce the results. The problem is, if you go back and you look at what the model is, this is an inverse model, where they're taking the observed craters and matching with the observed asteroids. But the actual asteroids keep going. They're actually there's another bump up here. You get to asteroids about 100 kilometers, and there's another excess of them out there. They actually probably the remnant of the original planetesimals that had that size distribution. And so if you include that in your forward model, turns out that there's no way to make the moon that looks like the asteroid belt. Because if you try to make the smaller craters match, you end up with what I call super Imbrium megabasins. So the biggest crater that we have SPA, but SPA is the first one, so it's not really relevant to this. I'll explain more if you want more details. Really, Imbrium is the one constraint. You can't get craters bigger than Imbrium in the time where you're cratering the moon with this. Imbrium is about 1,140 kilometers. So anything bigger than 1,100 kilometers violates that constraint. So it's the statistics, cratering is statisticals. You have to run many runs of this to kind of gather statistics. And what we find, though, is almost basically, except for exceedingly rare situations, you always get this sort of situation. You pepper the moon with these giant craters, and so the moon doesn't look like the moon we have. If you try to constrain it the other way, say, okay, we just don't allow any 1,000-kilometer craters. We'll stop the simulation as soon as you get something bigger than Imbrium, and you just don't have enough craters on the moon. The moon becomes very sparsely cratered. So there's a mismatch here in the population that made the craters and the main belt that we see today. There's two ways to interpret this mismatch. So either the material that actually made the ancient impact craters on the moon had way more small things in it, or had way fewer big things in it, or it's really no difference between those two things. So in fact, there was about 6 times more of this size impactor, about 20-kilometer impactor, in whatever this population that made the ancient terrains of the moon Mercury than what we see today. There's another thing that I've been doing with another student of mine who's been doing the cratering stuff, where we're actually trying to look at this discrepancy in these two models for the chronology of the lunar impactors. This is the foundational science that leads to how we date things on planets. So this is a pretty big deal. And if you look at the part of the lunar surface that has the best constraints, where you have really good terrains for counting craters and really strong constraints on the age of those surfaces that you count to those craters, which are the mare surfaces, you get a really big discrepancy between the different models that people use, where you should have the most consistency. So Stuart Robbins pointed this out in 2014, that if you just reevaluated the crater counts using LRO data that Neukomm didn't have access to, you find this much steeper drop off in the rate of cratering in the late Imbrian relative to this sort of the standard model. Now, one of the issues is that the standard model that Neukomm put together, the Neukomm production function, basically was amalgamating data from all across the moon at all different size scales, whereas the Mare are really restricted in both age and size and number density. So what sort of fits the constraints that we have on our isochron, or basically chronology functions for the moon that are really strong are only for these really small craters, really small impactors, versus the really big things. Okay, so put those two things together, that the chronology function seems to be really weirdly off for small things, and the ratio of small to big impactors doesn't seem quite right either. I think what's actually happening here is telling us that we're actually seeing two different populations. This is not one population making craters. There's actually two populations that had a very different kind of dynamical history. One is the large things that are making basins. Those basins are probing into the original planetesimal population that formed as part of the solar system's nebula that are being swept up at the end of planet formation. But in the meantime, you're creating collisional fragments for every time there's a big collision. Every time something hits Earth or Venus or Mars, you inject lots of little impactors into the space. And those collisional fragments are basically what are creating most of the small craters that we're using in our crater counts. So we've been trying to run some Fraggle simulations, some n-body, Swiftest Fraggle simulations for this. It's really challenging. It's just an example. This is that plot I showed with John Chambers, where they had this sort of very crude fragment population to show how the number of particles, it takes a little longer to make your planets. You do tune the parameters to make more realistic fragment populations, and the numbers are going up and they're never going down. In fact, they go up and up and up and up for like a few tens of millions of years before they roll back around again. So you actually, you get a lot of collisions, a lot of debris being ejected. So what we propose is that if you were to sort of look at the chronology of lunar impacts, the small craters that are showing this really steep decline in late Imbrium are actually probably probing a short-lived spike in some local impact. Something hits Earth, makes a big cloud of debris that then eventually equilibrates to the background over some time. Something hits Venus, something hits Mars. There are just collisions happening all over the place. We might just be seeing on the Mare surfaces that were sampled by Apollo, just one of these waves of small things that's basically being lost. Whereas this Neukomm's standard curve that's sort of matching across the whole moon is really sort of probing this background of these big planetesimals is constantly decaying. So you're not making new big planetesimals. They start with some number and they just go smaller and smaller over time. So you might have these populations are doing two different things over time, and that makes it really challenging to actually get ages out of this. So actually my long and short of this, if we're right, chronology functions are a mess. We might not actually be able to say much about saying what's going on Mars, the age of like when the Noachian and the Hesperian happened based on crater counts on the moon. It might not really hold together very well. All right, so the simulations unfortunately are very expensive. One of the things I want to do is actually work with Hal Levison to get LiPad connected up with this so that we're not just dealing with pure n-body, where we have the basic aspects of this to make the collisional outcomes with the right physics, but then the huge number of particles are handled by statistical code. You can see that this is a simulation that ran for many months, and only 14 million years in, and the number of particles keep going up because I'm just sweeping through. You get collisions that begin with Mercury and they kind of work their way out through the system. Okay, so I'm going to end there with, if you want to know more about the codes we use, tomorrow I'm talking about Swiftest. Wednesday I'm talking about Crater Maker, which is a newer code that's doing a landscape evolution model, but it has some really cool stuff with crater scaling and modeling size distributions, which you might find interesting. So come see me, and there's also, this links to the spreadsheet with the sign up. So if you find a spot, you want to talk with me, come see me. I'm here all week and I'm happy to meet. I'll even be here at Broadfest. So I'm actually looking forward to that. So if you want to meet at Broadfest, we could talk about what Broadfest was like in 2005 to 2009. And you have the other old timers tell you about what it was like. Spitali, I'm sure will tell you about before then. All right. So thank you for your time. And I'm happy to take any questions. If you have them. So. All right, I'm gonna tell you.
I have a question about the impact of external potential. So in the embodied simulation, for example, for the moons of Mars, is the potential dominated by the planet, or do you
Yeah.
account for the sun? And
So right now, yeah, we only include the planet as central body. So the solar effect's actually going to matter for long-term evolution of the ring, because you get into something that my colleague and good friend Matija Chuk loves to talk about, which is the evection resonance, which occurs due to a solar, basically a precession rate of your body starts to match the orbital period around the sun, and you get this like you can really drain angular momentum from the satellite moon, the satellite planet to the planet sun. So it actually relaxes our constraints on what the angular momentum of the Earth Moon impacting was, if you can have that happen. Anyway, long and short is, yes, that's actually a capability it's not actually hard. So, okay, one of the things I'm hoping to do is, as actually part of my sabbatical, is to recruit people to help us out with these. These are all fully open source codes, are on GitHub. Part of my thing in my workshop tomorrow is like, here's how you use the code, and I try to make it really user-friendly. It's all Python-based friends. You know Python, you don't even need to know Fortran to know how to run these, even though everybody's codes themselves are Fortran. All the interfaces are Python. But I would love to recruit people that would help us with some of the adding capabilities. One of them would be things like solar tides. Adding the sun as a perturber that's sort of fixed to go around and just acts as a perturbing body.
Yeah, specifically, I was thinking about Kozai-Lido.
Yeah, yes. Actually, the Kozai leadoff might be, so we're looking at two different mechanisms for how you get rid of the ring. One of them is a Kozai leadoff mechanism, where as the ring particles approach Mars, their inclination goes way up, and so then they become inflated, and so they don't behave the way our dense model. But the other thing, actually, the thing I think I'm more promising, actually, DPSC EPS, somebody showed me some results they're doing. There's a phenomenon called the Yarkovsky shaft effect, which involves, like, when you have a ring around a planet, you have a shadow cast on the ring. And so you get this Yarkovsky effect where the material going into the shadow is a little warmer than the stuff coming out of the shadow. And that can actually, depending on how the individual ring particle is spinning, that could actually cause them to collapse really rapidly onto the planet. So there's a couple of mechanisms we're actually exploring that involve solar effects. Okay, I think you had a question here too.
Yeah, so you gave a nice description of how important it is to have momentum conservation when you add in your collisional fragments. You don't want to introduce new physics, but how well understood is the distribution, right? I know you can do an integral, but you seemed confident that you could decide how to apportion it.
I'm not confident. No, I'm not at all confident. Maybe I came across as confident, but that's the thing about it. If you're a modeler's know all of the things that are wrong, all the shortcuts you had to take. Yeah, it's actually fundamentally it's a really challenging thing, because the thing that actually sets these parameters, like how much spin does a piece of rock have that's been tossed away from a collision, right? Well, if you really drill down to it, it's like all the electrical bonds and like how did the fractures go through the material and how and what terrain, what things they hit on the way. So it's like impossible but from first principles to work all that out. So you have to come up with some sort of empirical sort of best guesses for how to do something in a reasonable way. So to me, the most fundamental thing is that you're not introducing energy into the system. You want to make sure that you're not artificially injecting numerical energy, not artificially torquing the system up. To me, that was fundamentally important. How is that distributed? The only way to get out of there are things like the DART, like we're looking at some of the DART results to say how to do this. Looking at asteroid families, like just data, basically. We need to sort of see what the data tells us about what these things look like. And things like SPH codes. Like what is SPH? I occasionally go ask Eric, what do the things do that are leaving your domain? It's really hard. Some of these things are really hard to get at, but these are really important things. That's the way you're going to have to sort of whittle down the free parameters into something. I don't like free parameters. I want to, as much as possible, find data that can tell me how to set these things, so I don't have to fits with knobs and just let nature do its thing. Yes, no.
When you look at the interactions between a moon and a ring, how important is the dynamical friction between the moon and the ring?
There's not. Okay, so there's got to be dynamical friction as the moon is accreting from the ring. We actually see some of this kind of stuff happening in the sort of ratty outer edge of Saturn's main rings. You see like, where you see things like the propellers in like little, what do they call it? There's like little incipient satellites that are forming where the Roche limit is getting close to where you can actually stably accrete a satellite. But once the satellite forms outside the ring, dynamical friction is not the thing that drives it. It's Lindblad torques are what does it. And that comes from mean motion resonances between the satellite and the ring particles interior. Saturn's a great natural laboratory for rings, but it's also overly complicated because Saturn's this great big oblate planet with all these moons. So there's like all kinds of extra stuff happening in the rings. If you go to any ring session at like TPS, it's like, there's just so much going on. You got split resonance of the oblate terms, and you got, all this stuff happening that we don't really fully understand. It's much easier to work with like a Mars ring, where we actually don't have observations. Yeah, right. It's so much simpler, right? You don't have observations, complications. Here, and then Bill.
At your N-body work, I was surprised by some of your Chambers 2013 movies. Those early collisions should, at least in my own models of it, are pretty slow and shouldn't be disrupting quite as quickly, but it does seem like you're just instantly, immediately you have these pink and yellow colors.
Yeah, this is interior to Mercury. This is actually there's a paper that my former lab mate, good friend Kat Volk, who is around here, she worked with Brett Glyman on this called consolidating and crushing exoplanets. Actually, they were doing simulations like this of like even more interior to Mercury. And just because the velocities are going up, it doesn't take very much eccentricity inclination to get really spectacular impacts. So basically what's happening is that you're getting these kind of in this Mercury inwards of Venus zone, you're getting these super catastrophic collisions, which just start putting a lot of debris that kind of, causes cascade. Now, one of the things hard to see here is the sizes. I think I've tuned these down to get some particles as small as a kilometer. So a lot of these are really small fragments that are actually coming out of this. Part of the challenge is to actually try to find that sweet spot with modeling the number of fragments that you can actually get close to correct sort of evolution without bogging your system down in so many particles that everything grinds to a halt. Haven't quite found that sweet spot. I'm still sort of, that's why we haven't published this yet, because we don't know how to do this all the way to the end, because it's a little frustrating.
If I focus more at 1 AU at the lower eccentricities, then you can see some mergers are popping up. But
a lot of that's because you've got so much going on inwards. You're just creating these waves of particles that feed back on themselves. Yes, Bill.
So my information may be obsolete, but I thought I remember a report that Phobos orbit was decaying.
It is, yes.
Yeah. So how does that fit into your scenario?
So that's basically one of the outcomes is this decaying, because it's going to turn into a ring before too long. So if I go back to so watch how Phobos, see every time you make a Phobos progenitor, once the ring starts to go away and if the ring collapses, you're always going back, right? So actually in about 50 to 70 million years, there was a Tushar Middle and Benjamin Black had a paper where they showed that it's probably not going to make it all the way to the surface because it's a rubble pile. It's a gravitational aggregate. It has to have some cohesion, some not a lot. It just has to have some amount. But we just say, okay, when it gets this close to Mars, it'll break up into a ring. And actually, Harrison Agrusa has been started to work with us. He's actually shown us that it might be more dire than that. You actually don't have to make Phobos go close enough to tear it apart. You just have to get it close enough that if an impact happens on Phobos, the material is already barely held together, that the impact will actually initiate the Sesquinary Catastrophe at Phobos. So the Sesquinary Catastrophe might actually happen to destroy Phobos kind of through this collisional cascade before the Roche forces sort of tear it apart in sort of like an isolated sort of Roche limit kind of situation. What we're thinking now is that the Sesquinary Catastrophe might just be a generalization of the Roche limit. So as you get close to the Roche limit, the threshold for initiating a Sesquinary Catastrophe approaches zero velocity, right? And so because basically imagine like you're on the surface of of a moon that's so close that the tides are kind of barely holding together, little ping, little impact, and that material is going to leave, and then it'll process around and collide again and cause a cascade. So it actually might tear itself apart a little further from this line that we suggest.
So you're not really arguing for a special moment in time where we're lucky to see Phobos. This is actually a cycle that's
Yep.
repeated.
It's just you're in one phase of the cycle. Yep. Yeah, that's one thing I really love about that. I mean, there's no reason why Phobos, we couldn't be seeing a spectacular coincidence of Phobos being the last, 1% of its life. Just like the moon is the same parent size in the sky as the sun. There's no reason that happens. It's a coincidence. We're living in that time. But it's kind of nicer when you don't have to say, oh, it's just we're in a special time where if we waited 100 million years, there'd be no Phobos to observe. But what we suggest is, we're just in the time where it's on its way to being a disk. The dinosaurs would have seen it like forming out of a disk, right?
And I've been a fan of this model for some time.
Oh, thank you.
Yeah.
It's great to find fans out in the wild. That's great. Usually it's just my students tell me they like it, and they have to. So
Yeah, it's really fun. The one criticism I've seen in literature and question I haven't answered in my own head is there does seem to need to be some special time where we are today, where there is not a
no ring.
There is no ring.
Yeah, so that's why I was really excited. There's a guy named Wenhan Zhua who's he was at Nice, but now he's got gone to Tokyo. He was actually showing me this Yarkovsky-Schaff result, and it's really cool because what happens in his model is that there's a threshold size surface mass density that you hit, and once you hit it, the ring actually collapses back into Phobos, like really quickly. So it's basically a threshold event. So basically, once you kind of make your initial ring and you sort of spread it out and you start making a new satellite, really pretty quickly you get this situation where the surface mass density gets low enough that your Yarkovsky-Schaff takes over from viscous spreading, and the whole thing collapses onto Phobos. I really like this. I'm hoping that turns out to be the one fly in the ointment. There is that requires a certain spin state of the rings, and none of the Cassini ring people can tell me what the individual ring particle spin distributions are, because although it's important, they don't know how to really constrain this. If they are they're spinning with a sort of an inertial space, like they're not tidally locked, then this works. If individual ring particles are tidally locked, then it goes the other way and everything goes inwards instead of outwards, and thing gets a little more complicated because then you get rid of too much mass too quickly. So stay tuned for that. I'm hoping he's going to work on that and publish that. We'll have a paper on that in a year or two. So stay tuned.
Well, any last questions? David's here the whole week. I could stay here all day and ping you with questions, but we're going to be doing this later. Yeah, there's the QR code if you want to meet with him. I found this really fascinating. I have about 7 questions to ask you later.
Only 7? Eric, that's not like you. You have like 12 ideas and 7 questions like that.
They're kind of holographic.
Yes. All right.
All right. Thanks a lot, David.
All right. Thank you, everybody.